Welcome, everybody, to the Flowing Through Southern California, or Flowing Through SoCal video podcast. Today, I have a great guest to talk about PFAS and what this means moving forward in the environmental industry. JP Verheul with Enthalpy Analytical Laboratories is joining me today as my guest to talk to this subject. It's a very hot topic right now, and there's a lot of interesting things that are wrapped around this. So, JP, give me just a little bit of background on what you do and what your role is, and then we can start with the PFAS discussion.
Sure. Thanks, Sean. It's great to be here, and I really appreciate the opportunity to share more about what we've learned about PFAS over the years. So I'm a senior chemist with Enthalpy Analytical, and I lead our national technical solutions team for PFAS and UltraTrace. So what we do is we work with our PFAS laboratories to help provide various analytical solutions to folks that are looking to evaluate and measure PFAS in the environment, looking at samples of drinking water, groundwater, wastewater, solids, biosolids, air, you name it. So that's basically what I do.
Okay. And you manage one of the laboratories, I suppose?
So I work more on the business development side of things. We have two Department of Defense accredited PFAS laboratories. I work very closely with our sales team and with the laboratory directors of both of those labs to help optimize the lab services for our clients' projects.
Gotcha. Okay, great. So tell me a little bit about PFAS. What is a PFAS and where are they found?
Sure. It's a loaded question, right? So PFAS stands for per and polyfluoroalkyl alkyl substances, and I've got some slides that we can kind of sing along to. But basically, these are fluorinated carbon compounds that have been around for about 75 years. When we talk about PFAS, really what we're talking about is a class of chemicals. And what defines this class is a common theme of a carbon backbone, so a certain number of carbon atoms that we can see here that are all that may all or may have some bound to a fluorine atom with a functional group like a carboxylic acid or a sulfonate. And what we see is that depending on the length of the chain, the number of fluorine atoms that are on the chain and the different functional groups, these chemicals will have varying properties and also varying levels of health effects or other effects, right? So the first application actually for a PFAS compound was in the late 30s. It was military application of Teflon, which was developed for the bomb, believe it or not. We saw a commercial production in the 40s, again for Teflon, which led to the era of better living through chemistry, right? And over the following 75 years, there were a number of different chemicals that were produced for varying purposes. So we've got aqueous film forming foam for firefighting purposes, waterproofing. These are used in dielectrics and hydraulic fluids. So a wide range of compounds, wide range of applications is really what we're talking about.
I think I read somewhere that PFAS are contained in like our waterproof jacket, like Vortex, and lining in coffee cups, for thermal lining and things like that for like coffee cups from your nearest coffee vendor.
Yeah, it's all over the place. So certainly food packaging is something that, it is a big problem with a lot of PFAS compounds. You think about the pizza boxes or the burger wrappers that grease doesn't get through. Well, that's because they're lined with PFAS, right? And to your point, a waterproof material, it's all got a PFAS chemical ingrained in the threads. Couches, right? Everybody loves their stain-proof couch, right? Well, that's PFAS right there. So it's all over the place. And that's sort of what makes this a real challenge for us to deal with when we talk about PFAS in the environment. Lots of contributing sources, right?
Right. And if we're taking our food and beverage and putting it, exposing it to PFAS, then we're eating it, then theoretically that's the exposure pathway. So are these are acutely or chronically toxic to humans? So maybe talk a little bit about what the findings are that sort of prompted these drinking water standards. Like, talk about the health, bad health effects of these to humans.
Sure. So I think it wasn't until the 1980s when the U.S. Navy found that aqueous film forming foam was having deleterious effects to aquatic life. And shortly after, we found it in the blood of most folks. there was a study that was done, and in fact, there's a documentary out there, "The Devil We Know," that does a pretty good job of outlining cancer cluster in the Ohio River Valley from the production of these compounds. We talked about this as a class of compounds, so tons of different chemicals here, but there are some that are known to be carcinogenic. And the EPA has done studies and has published some information about peer-reviewed studies out there that reflects some of the dangers here. So, we're talking about reproductive effects, right? Decreased fertility or high blood pressure in pregnant women, developmental delays in children, low birth weight. There are some increased risks of other cancers and reduced ability for the body's immune system to fight infections. This is all directly from the EPA. And then, of course, concerns with hormones, right? Is this an endocrine disruptor? There are tons of ongoing studies right now. And because this is such a wide range of compounds, we really don't have that much information about the toxicological effects of all of them. I think that's part of why we're seeing the EPA respond to PFAS the way they are. We know that there's a big potential for damaging health effects here, but it's really difficult to quantify without more information.
So the EPA has set these drinking water standards, right? Talk a little bit about what that number is and maybe how they came up with that number.
Yeah, it's all about risk assessment. I think the EPA would have put these numbers would have put them much lower if they could, but we're really limited by some of the analytical technology. So, we're talking about here the maximum contamination limits, right, that the EPA recently released for 6 compounds. The limit for 2 of these is 4 parts per trillion, which is insanely low. I mean, that's, less than a grain of sand in an Olympic-sized swimming pool. Prior to that, the EPA had actually released a health advisory limit for one of these compounds at 4 parts per quadrillion, which is extremely difficult to detect. I think they would have put these limits as low as they could if it hadn't been for some of the restrictions and the analytical capabilities at the time. So again, looking at conservative approaches when it comes to risk really is, I think, how these numbers came to be.
So just for context, that 4 parts per trillion, if I was to take, and that would be coming out of the potable water treatment plant, right? That limit is for right there, and then it goes through the piping and distribution system and shows up at my spigot, right, or my sink. So I open that up, and let's assume it's still below the 4 ppt, and I put that into a cup that has a PFAS liner in it, and then I drink that water. Is the potential there that water that I'm drinking exceeds the 4 ppt now?
Yeah, it's a murky question. Anything is possible. What you're really talking about there is the leachability of PFAS, right? And that's one of the big concerns we have when we look at environmental samples. If I'm cooking with a skillet that has Teflon lining, what are the chances that I'm going to have PFAS break off of that pan and enter my food, right? Not a lot of great data on this, but to your point, it absolutely could be possible. And that's, I think that's one of the things that has people spooked about PFAS. Going back to the MCLs, there are kind of, since we're talking about the effect of PFAS in aggregate, there are some quantitative limits for these, right? 4 ppt for 2 of these compounds, 10 for others. There's also a hazard index, right? And so this hazard index is a way of calculating in aggregate the potential danger from these different compounds based on their concentration. So the EPA has a formula, and I've got a slide here for it, where you analyze these different compounds, you quantify them, and then you run those concentrations through a formula. And if the number you get when you do that is 1 or greater, you've got a real problem. That's the hazard index. If it's below 1, then would say you're in good shape. So all that to say, you could have instances where you're actually below the threshold for some of these compounds, but you end up with a higher hazard index based on the concentration of others.
So these are so pervasive, in our world right now. I'm imagining surface water being impacted with it, subsequently groundwater being impacted with PFAS. Stormwater, that's an issue too, right? If there's PFAS in and around, then presumably it could be integrated into stormwater, and then we know it's in wastewater as well. So of those 4 different sources of water or mediums of water within, what are the implications for the fate and the transport or how, describe the fate and transport of PFAS, across those different pathways.
That's a great question. And it is really helpful to think about it in those different categories of exposure, right? So groundwater, wastewater, surface water, and stormwater. So with stormwater, obviously you're worried about runoff, right? And that runoff could then lead you to a surface water situation. A lot of drinking water plants do use raw surface water as their source for final treated drinking water. Many of these plants are not built to treat for PFAS. So, the surface water and the stormwater is certainly a source of contamination for our drinking water. We talked about the MCLs, and what's so interesting is, the MCLs are there for drinking water, but by establishing those, we're really creating the need for remediation efforts in these other areas like surface water, stormwater, groundwater, and general wastewater. Certainly groundwater is going to be a concern. PFAS is highly mobile. So, it may be a great example is land application of biosolids, right? We've seen instances where biosolids that were contaminated with PFAS were land applied, and then that's been linked to groundwater contamination. Certainly waste disposal or improper disposal has led to PFAS in groundwater. And a lot of water utilities use groundwater as their source water. So that, again, is another exposure pathway for this. And then, of course, wastewater, right? So we talked about surface water and stormwater. I live in Richmond, Virginia, right? The Richmond drinking water system is basically pulling water out of the James River. We're all drinking Lynchburg's treated effluent, right? It's up the river from us. This is pretty common across the country. Many of these wastewater plants are not suited to treat for PFAS, and so it ends up in the drinking water. But it's not just the municipal wastewater plants we look at, it's industrial dischargers, right? Manufacturing facilities that may either manufacture PFAS or utilize PFAS chemicals somewhere in their manufacturing process that then discharge into a river or a creek or other water system that is now contaminated with PFAS. And kind of to build on to that, we have seen some movement with NPDES permits, the National Priority Pollution Discharge Elimination System permits that will target some of these. Those permits are really only looking at a subset of compounds, right? About 40 compounds in what we call method 1633. And you can have a situation where one of these manufacturing facilities may show that they have removed the compounds in this list of chemicals, list of 40 chemicals, but there may be other PFAS like ultra short chain compounds or precursors that are not detected, that are discharged and ultimately will form terminal PFAS chemicals once they hit the wastewater treatment system. So kind of a long and convoluted answer, but it's a complex question. So.
Right. And Black & Veatch certainly is in the space, and the wastewater space. We've got a number of clients where we're doing assessments like what you described, with understanding the PFAS, fate and transport through the wastewater treatment system itself. Interesting. And so from the laboratory perspective, let's talk a little bit about the analysis. So I suspect the first thing that would need to happen if I'm going to submit a sample for PFAS concentration, right, I need to collect that sample. So I'm just imagining if these materials are all over the place, and I remember sampling using Teflon lined sample tubing for automated samplers, and some of our equipment like the Teflon jar lids, liners of lids, and things like that for analytical equipment. So talk a little bit about how you sample for PFAS in a way that you're not contaminating the sample with PFAS.
Yeah, that is a great question, Sean. So it is everywhere, and the way that you sample is really important. Preparation is everything. So on the laboratory side of things, we use polypropylene containers. You're right, Teflon line lids are ubiquitous. The laboratory that I used to work in as a chemist, we only use Teflon line lids, right? It makes a great seal. Certainly not an option for PFAS. So we look at polypropylene containers. And then really, it's about what you're wearing when you're sampling. So we suggest cotton clothing, acrylonitrile gloves, not latex gloves. There are many PFAS-laden sunscreens, perfumes, makeup, hair products that are out there. So it's really important to do an evaluation of what you're wearing when you go out there. Bug spray, right? I mean, who wants to sample in July in some of these areas with mosquitoes and have PFAS bug spray, right? So that's a real concern. And what we suggest is, in addition to the right type of material that you wear, collecting the proper field quality control samples. So examples would be a field reagent blank, an equipment blank, something like that. And in order to do that, you need to have PFAS-free water, which you can usually get from your laboratory, or which you may be able to generate yourself and send into the laboratory for confirmation testing. So,
okay. Yeah. So if I'm doing a field blank, so I'm using laboratory, triple milliquat deionized water.
That's right.
And if I collect that field sample and that goes in with my sample to the laboratory, if that has PFAS in it, my field blank, then that would somehow describe perhaps there's PFAS flying through the air at my sampling environment. And so now I know that my results I get back from the sample that's submitted from the wellhead, for example, some of that could be, from the housing in which I've collected that sample. So that seems like a good reason to have a field blank and equipment blanks and things like that as well, just to ensure that there's no PFAS being added to the sample. So, okay, so then you receive the sample, and then tell me about how the laboratory goes about analyzing that sample. What are the methods and the equipment that's used and some of the prep? And then also talk about some of the QC along the way to ensure that within the laboratory setting, there's no additional, PFAS that shows up in the sample result.
Yeah, it's great. I love it. So I'll start with the second part of your question first and talk about how do we prepare the laboratory, because to your earlier point, right, it's everywhere. So we have to do a tremendous amount of work to make sure that we are not introducing contamination in the laboratory. So we look at we lot check all of our containers, certainly all of our reagents, the PFAS-free water that we produce in the laboratory. We're also looking at all of the reagents that come in. And it's interesting, during COVID, of course, I think we all remember that there was a real crunch on the supply chain. And so what that meant for us is that we had to expand the number of vendors that we have. It also means that we have to be careful about lead times to get containers. So at any point, we may have 1,000 different containers in the lab, all of which we have to lot check separately. So a lot goes into how we manage things inside the laboratory to avoid introducing any kind of contamination. Once the samples come in, then the real fun begins. So the most common methods that are out there, there's two drinking water methods EPA 537.1 and EPA 533. And then, of course, there's methods 1633, which was just finalized at the end of January, which is for basically everything else, right? Your non-potable water, so your groundwater, wastewater. It's also for sediments, tissue, biosolids, solids, things like that. All three of these methods utilize the same type of sample preparation process, something called solid phase extraction. So solid phase extraction basically involves taking a solid phase media. We use something called weak anion exchange media, and then running the sample through that media, right? And so I've got a slide here that kind of shows what that looks like. The sample flows through the media, and the idea here is that the liquid phase goes through the media and all the PFAS are captured onto the solid phase media. So once we run the entire sample through that media, we will then extract the PFAS from that media with a solvent, methanol, right? So we'll use methanol to liberate the PFAS from that media, and then we will concentrate that methanol into a very small aliquot. This is one of the ways that you're able to achieve such incredibly low reporting limits and detection limits. You're taking a large volume of water, and then you're concentrating it down into a very small amount of final aliquot of solvent. At that point, that sample, right, the aliquot of methanol, is introduced into the analytical instrument. And the instrument is a liquid chromatography mass spectrometer. And so the way that this works, and again, I got some photos here of the column. There is a liquid chromatography column that serves to separate out the different PFAS compounds over time, right? So the sample flows through the column. the different compounds separate out as they elute or come out of the column onto a mass spectrometer. And it's actually two mass spectrometers. The first one serves to ionize the sample, which really means to blow it up, right? So breaks up the sample into different pieces, and then those different pieces have different masses and different charges, will land on a second mass spectrometer, which serves as the actual detector. So really what we're doing in the laboratory when we're analyzing this is we are looking at the different fragments of the individual PFAS molecules as a function of not just the mass to charge, but also the time component of when they come out of that column. And that's really the crux of the analysis at a high level. So you'd asked about QA/QC. There's another really important component to this. It's not part of 537.1, but it is part of 533 and method 1633. And that's something known as isotope dilution. So I got a slide here that kind of does a good job of refreshing what isotopes are. So isotope dilution, if anybody listening to this doesn't remember anything, I hope they remember just this, that isotope dilution is the gold standard for PFAS analysis. When we talk about isotopes, what we talk about are, in this case, carbon, right? We talk about different forms of carbon atoms. So carbon-12 is the most abundant form of carbon in the world. It is 99% of all carbon that we have is carbon-12. It's 6 neutrons, 6 protons. 6 and 6 is 12, right? There is an isotope of this, or another form of carbon, which has 6 protons and 7 neutrons. That's carbon-13. There's also carbon-14, but it's very unstable, doesn't really matter for the purposes of this talk. Carbon-13, because it has that 7th neutron, is just a little bit heavier than carbon-12. Why does that matter? That matters because we can leverage that difference in mass when we perform an analysis. And the way that we do this is by adding what we call radioisotopically labeled standards. So I've got here a slide that shows 2 molecules of PFOS. Both are PFOS. The main difference here is that one is your synthetically manufactured PFOS that we find in the environment. The other is an isotopically labeled standard. It's just a little bit heavier than the carbon-12 PFOS. What we do in the laboratory is when we receive your samples, we add a very small amount that we know, right? A known amount of the carbon-13 or radioisotopically labeled standard directly to the sample before we do anything. So we introduce that is our external standard. And we know how much we add, and I've got a great flow chart here that kind of helps explain the process. So let's say we've got an unknown amount of PFOS. Let's say it's got 100 nanograms of PFOS in your sample. We don't know that, but that's what's in the sample. And we will add 2 nanograms of carbon-13 PFOS. So it's a 50-fold ratio, right? 1-to-50 ratio. So we know how much carbon-13 PFOS is in that. We then take that sample and run it through the entire analytical process I just described. So we take it through solid phase extraction, we clean it up, we concentrate the methanol, and then we analyze it. And when we analyze it, we see, okay, what's our PFOS concentration? Okay, it's 25 nanograms. And then we look at our carbon-13 concentration and we say, okay, it's 0.5 nanograms. But we put in 2 nanograms, we're only seeing 0.5. That means we saw a reduction of 4-fold in PFOS, right? And so we can then infer, right, with a high level of precision, what the actual carbon-12 PFOS concentration is. If we know that we've got a 4-fold suppression there, we're only seeing 25 nanograms, we have to multiply that by 4 and we get 100 nanograms, right? So hopefully the flow chart helps a little bit, but that's really the analytical process in a nutshell. It's complex, but it is highly effective and allows us to perform this analysis at a very high level of precision when we're looking at very low concentrations of PFAS.
Interesting. There's a whole process taking me back to my days of chemistry. I took chemistry classes, obviously, in college as part of my education.
I hope nobody's having terrible flashbacks to high school or college chemistry right now.
Yeah, absolutely. So, and then I've also heard these PFAS referred to as the forever chemicals. And just talk a little bit about how we would go about removing these from our drinking water source, for example. What does that process look like?
Yeah, that's great. So we do a lot of work in the PFAS treatment and destruction spaces, and I'll tell you, Sean, one of the most exciting things about PFAS right now, it's a lot of doom and gloom, but I think the silver lining is that we're getting to see some of the brightest minds in the fields of chemistry and treatment come out and do things that we've never seen before. So when I think about treatment and destruction, I think about it in those two different buckets, and maybe treatment is the best place to start. So we've got the traditional old treatment technologies out there: granular activated carbon, ion exchange, resin, and reverse osmosis. All three of these technologies will remove some PFAS, but no one of them will remove all of it. So when we talk about activated carbon, it does a great job of removing some of the longer chain PFAS, C5, 6, 7, 8, right?
Okay.
The short chain compounds like TFA or maybe smaller compounds, they fly right through. So if you've got activated carbon, you're removing these heavier compounds, right? Including the ones that, fit the MCLs, but you're not removing everything. Ion exchange is great. Ion exchange can remove much more, but of course it has its own challenges. It will remove other things. So you can have other constituents in the water, maybe non-PFAS chemicals that suck up those binding sites in the resin, right? And then of course you've also got a waste component, and you have a waste component with activated carbon as well.
Sure.
Reverse osmosis is certainly fantastic, but as you and I'm sure most of the folks listening know, you've got a waste component in the membrane and the concentrated brine, and also you're going to be limited as to the type of matrix that you can actually treat, right? So something that's very chemically rich and full of solids and maybe high dissolved solids and total solids may not be ideal for something like that. So those are the most common things we're seeing. Now, when we talk about destruction, there's one other treatment, which is foam fractionation. I'm seeing a lot of this in landfills. This is super exciting stuff. So PFAS, we know, is a surfactant. That's why it's such a great firefighting foam, right? It's naturally a surfactant. You can use that property to sort of remove some of the PFAS. So there's this process called foam fractionation where you basically run bubbles, right? Like in a fish tank, just run bubbles up through your water, and the PFAS will actually rise to the top and in some cases foam up, and you can remove the foam, and then the effluent at the bottom will have a lower concentration of PFAS. You can do that in series, right, and remove quite a bit of PFAS. So when we talk about some of these chemically rich matrices, like landfill leachate, for example, foam fractionation has been shown to remove quite a bit of PFAS, which is sort of exciting. Now, you still have a waste component, but it's there, and it can be used with some of these other technologies to achieve massive reductions greater than 99%.
So maybe, putting all of those together, right? To
exactly.
remove all of it. Yeah.
Sure. And so
this is super interesting. It's a whole world, right? And I feel like we're really in the beginning phases of this thing. So where do you think we're going with all of this? I mean, what do you see sort of as the future if you were to project now 10, 15, 20 years down the road? What are we going to be looking at for treatment systems and additional regulation and things like that? Where do you see this going?
Sure. That is a loaded question. If I had a crystal ball and I could tell you the answer, I'd probably be a wealthy man. But I think when we look at PFAS, when we look at the future of it, the things that we can say for sure are we've really only scratched the surface. There are thousands and thousands of these chemicals, and that method 1633 that I mentioned, it's only targeting 40 of them. I mean, we only have MCLs for 6 of these. We really don't have our arms around what the toxicological effects are and what the real presence in the environment is at this point. So it's hard to say. I think what we're going to be looking at is more toxicological studies. We're going to be looking at larger efforts for environmental site assessment and remediation, expanding regulations, right? So we've got a little bit now with the MCLs and with updates to CERCLA and RECRA, but I think we'll see more updates as we get more information, and then I think we'll see more movement in the actual removal of these compounds in the environment, and also the destruction, right? And that's really the exciting stuff, is talking about how do we actually destroy this in a way that is economical, cost efficient, and effective.
Yeah, so certainly a future among multiple fronts with this, right? From characterization and analysis to figuring out ways to get rid of it, and then ways to ultimately get rid of it because now it's stuck to your media that you just used to remove it. So it's certainly certainly some things to think about. And I guess there's the good news too, right? I mean, the good news is, like you say, there's lots of people working on this, and the future looks bright, and ultimately we'll get to where we need to get to. But so it's like this with lots of different things, right? We used to think asbestos was great, and and then we learned things, and there was a whole industry that wrapped itself around the removal and remediation of those materials. So this has been great. I've learned quite a few things today, particularly with respect to the laboratory methods, which I always wondered about, how you're analyzing these things for PFAS concentrations. But again, thank you, JP, for joining. This has been very good, and we may have to circle back and do another one of these as more regulations come online, and we talk more about different changes to methods even in the future, and detection limits. So again, thank you so much for joining me today, and have a good day.
Thanks a lot, Sean. Happy to do it, and you do the same. Appreciate it.
Thank you so much.